This lesson is on mass-mole reaction stoichiometry. So what I would like you to do is answer these three questions. So pause the video, work them out, and then come back and we'll see how you did. So go ahead, pause the video and work the problems. Okay, hopefully you're back. And our first question was an easy one. How many moles of zinc are in 25.0 grams of zinc? So we do our dimensional analysis. X moles of zinc equals 25.0 grams of zinc times our conversion factor from the periodic table, 1 mole of zinc divided by 65.38 grams of zinc. Grams of zinc cancels out. Our unit is moles of zinc. And then we have our answer, and notice we have three significant figures. 25.0 has three sig figs. When there's a decimal point, we go to the end of the number, so that 0 is important. And then we have 4 sig figs there. That 1 is unlimited, so 3 sig figs. All right, our next question was to write the balanced chemical equation. And here is our answer. So we have solid zinc, aqueous, hydrogen chloride, hydrogen +1, chloride -1, cross your charges, HCl. Now, when hydrogen chloride is aqueous, it is called hydrochloric acid. So when you pour some hydrochloric acid on some zinc metal, you end up with hydrogen gas. Notice this is H2. Remember, hydrogen is a Hofbrinkel that you must use the subscript 2 when hydrogen is in its elemental state, when it is by itself in a chemical reaction. I've noticed that many of my students are forgetting the Hofbrinkels in chemical reactions, H2. Plus zinc chloride, zinc is 2 plus, chloride -1, cross our charges, and our formula is ZnCl2, and that is aqueous. And then our ratio is 1 to 2 to 1 to 2. And our next problem, we also have zinc, but now we have hydrogen phosphate. So phosphate is a 3-, hydrogen's a +1, so our formula is H3PO4. This hydrogen phosphate dissolved in water is known as phosphoric acid. So now we have a different acid, pour it on some zinc metal, and you still get the hydrogen gas, and now your other product is zinc phosphate. Ooh, that zinc phosphate would be a solid. That would not be aqueous, that would be solid. All right, but that doesn't matter for the balancing. So our coefficients now are 3 to 2 to 3 to 1. So I wanted to make the point that we could take this 25 grams of zinc and pour on some hydrochloric acid and have this reaction happen. Or we could take that same 25.0 grams and pour on some phosphoric acid and have this reaction happen. But to get the moles of the zinc, we did not look at the coefficients of the balanced chemical equation. We didn't need it. And now that we've been doing mole ratio, remember that when you do molar mass, that is always for 1 mole. And you only use the coefficients when you are doing mole ratio, such as 3 moles of zinc for every 2 moles of H3PO4. So that's going to be really important going forward. All right, so let's look at our first problem today. How many grams of magnesium are needed to produce 155 moles of titanium when titanium Roman numeral 4 chloride is reacted with magnesium to produce titanium and magnesium chloride? All right, so there's a lot of chemistry going on in this problem. First, we're going to write our balanced chemical equation, then we'll do the stoichiometry. So now we have to figure out our reactants and our products, get the formulas. You guys know how to do this part of it. All right, so titanium Roman numeral 4 is reacted with magnesium. There are our reactants. Titanium, Ti, Roman numeral 4, 4 plus, chloride, -1. There is our formula. And you may remember that they call this tickle in industry. Okay, that's our first reactant. Our second reactant is magnesium. That's just magnesium metal. when magnesium in its elemental state, it does not have a charge. It only has a charge in compounds. To produce, yield sign, titanium. So titanium as a metal in its elemental state does not have a charge. It has the same number of protons as electrons. And magnesium chloride. So magnesium is a 2+ ion, chloride -1, cross our charges, and we get MgCl2. So now we can go ahead and balance it. Titanium, we have 4 chlorines, we have 2, so we're going to need a 2 here, and that means that we need 2 magnesium there. So there's our equation. And again, if you want, you can do the titanium, the chlorine, and the magnesium and list your atoms and balance that way. Or at this point, you've balanced a lot of equations, you may just be able to do it like that. All right, now we're going to go ahead and go back and read the problem and put our information underneath the appropriate substances in the balanced equation. So how many grams of magnesium, there's our x grams, are needed to produce 155 moles of titanium? 155 moles. All right, so now we just need to do our dimensional analysis. So x grams of magnesium equals 155 moles of titanium. Multiplication sign and crossbar. So we want to go from titanium to magnesium. We have moles. We're going to use mole ratio to do that. So our mole ratio is 2 moles of magnesium for every 1 mole of titanium. Cancel out the moles of titanium. As I mentioned earlier in a previous video, it's very important to put the substance after the unit so that we can properly cross out the substances. So now we have 2 moles of magnesium. We're not finished though, because our problem wants the grams of magnesium. So we need to do another conversion factor. We want to get rid of the moles of magnesium and get to grams of magnesium. Well, that's just molar mass. So we look at our periodic table under magnesium, and we see that we have 24.30 grams of magnesium in 1 mole of magnesium. Cancel out moles of magnesium, and now we have the unit. Everything is canceled out except grams of magnesium, which is what we want. Put in our equal sign and our unit, grams of magnesium. And now we multiply any numbers in the numerators, divide by any numbers in the denominators, and 3 sig figs, unlimited sig figs for mole ratio, and 4 sig figs. So our answer, we get 3 sig figs. So let's calculate that. 155 times 2 times 24.3. And we get, let's write this down. We get 753. Now, we need to write that with the right number of sig figs. We only need 3 sig figs, but we have to maintain the magnitude. This number is in the 7,000s of grams. So 7,530 grams of magnesium is the answer here. That 0 is a placeholder, and this shows 1, 2, 3 sig figs. Remember, when there's no decimal point, you stop counting when the rest of the digits are zeros. So it's all about setting up your problem carefully and using the appropriate conversion factors. We only use the coefficients when we have moles in the numerator and denominator for mole ratio. Whenever we're doing grams to moles, it is always for 1 mole of a substance. We learned how to do molar mass before we've even learned how to do reaction stoichiometry. You don't use the coefficients when you're doing molar mass. Okay, so let's do another problem. How many moles of water are produced when 2.24 grams of methane are burned? Now, when we see that word burned, this means we have a combustion reaction. And not just any combustion reaction, we have combustion of a hydrocarbon, which is methane. So we'll write our equation. So methane, CH4, if it's combustion, we must have oxygen as a reactant. And notice I write O2, not O. Oxygen is a Hofbrinkel. We must write it as O2. 2 produced. Now, whenever you have combustion of a hydrocarbon, your products are CO2 plus H2O. So we learned that a while back when we were doing the different types of reactions. Complete combustion of a hydrocarbon always gives you CO2 and H2O. So now that we have all our formulas, we can go ahead and balance. And this is a CHO, carbon first, then hydrogen, then oxygen. 1 carbon, 4 hydrogen, I need 4. And now I have 2 plus 2, a total of 4 oxygens. On the right, I need 4, put in my coefficient of 2. Now we can go back and put our information into the problem. So how many moles of water, X moles, are produced when 2.24 grams of methane are burned? Now we can do our dimensional analysis. X moles of H2O equal our quantity of interest, 2.24 grams of CH4, multiplication sign, and crossbar. Now, this problem is a little different from our previous problem. We're starting out with grams of methane. We want to get to moles of water. To do that, we're going to need the mole ratio. So we need to turn this into moles. So our first step now is to do a molar mass calculation to turn the grams of methane into moles of methane. So 1 mole of CH4, well, we got to calculate how many grams of CH4 are in 1 mole. So we can do that off to the side. So we have 1 carbon, and we have 4 hydrogens from our periodic table. Carbon's 12.01, hydrogen is 1.008. Let's figure out the molar mass. 12.01 plus 4 times 1.008 equals, and we take that to 2 decimal places, so we have 16.04. Remember, this is the grams in 1 mole. Whenever we do a molar mass calculation, it's always for 1 mole. So our number that we put here is 16.04. Now the grams of the methane cancel out, and we have moles of methane. Now we use our mole ratio from the coefficients. And our coefficients let us know we have 2 moles of H2O for every 1 mole of CH4. Cancel out the moles of CH4. We're looking for moles of H2O. We have the units of H2O, so we can put in our unit. And now multiply any numbers in the numerators, divide by any numbers in the denominators. So we have 2.24 divided by 16.04 times 2 equals, and check sig figs, 3 sig figs, 4 unlimited, so 3 sig figs, so our answer is 0.279 moles of H2O. Okay, then we have one more problem to do. And this is the big one. All right. So now our problem says, determine the number of grams of sodium phosphate necessary to react with calcium nitrate to produce 15 grams of calcium phosphate. Sodium nitrate is also a product. All right, we need to write our balanced equation. So sodium phosphate and calcium nitrate are our reactants. So let's get that formula. So sodium is a +1, phosphate, PO4 with a 3 minus charge, cross the charges. Our first reactant is Na3PO4. Plus, our second reactant is calcium nitrate, Ca2 plus NO3 minus, cross, cross. We had Ca parentheses NO3 parentheses 2. Yields are products or calcium phosphate. Calcium 2 plus, phosphate 3 minus, cross, cross, Ca3 parentheses PO4 parentheses 2, plus sodium nitrate is also a product. Sodium plus 1, nitrate minus 1. So our formula is NaNO3. All right, now we need to balance. And since we have polyatomic ions, we can balance them as a group. I'm just going to put parentheses around these. All right, so let's see. 3 sodiums. I'm going to need, oh, you know what? I'm just going to do this quick. I know I'm going to need 2 phosphates. I'm going to put a 2 here. That means I'm going to need 6 sodiums. 6 nitrates. I'm going to need 6 nitrates. Put a 3 here. And I think I'm balanced. 6 sodium, 2 phosphate groups, 2 phosphate groups, 3 calcium, 3 calcium, 3 times 2, 6 nitrate groups, 6 nitrate groups. So again, I know that was kind of fast. You might want to list everything down and do your atom counts and balance that way. Okay, so now we go back and see what we need to calculate. Determine the number of grams of sodium phosphate. All right, that's our X. Necessary to react with calcium nitrate to produce 15 grams of calcium phosphate. Okay, so now we will do our dimensional analysis. We're going to do it way over here, start way over on the left because we're going to need 3 conversion factors for this one. So X grams of Na3PO4 equals 15 grams of Ca3PO4 2. Multiplication sign and crossbar. Starting with grams, first thing we're going to do is change those grams to moles. In chemistry, we're almost always changing grams to moles. So we need to do a molar mass calculation to get the grams in 1 mole. So I'll do that down here. So calcium, we have 3, phosphorus, we have 2, and oxygen, we have 8. So calcium is 40.08 from the periodic table, phosphorus 30.97, and oxygen 16.00. So we're going to add them up. So 3 times 40.08 plus 2 times 30.97 plus 8 times 16 equals. So I'm getting 310.18. So that is the grams in 1 mole. So 310.18 grams of Ca3PO42 are in 1 mole of Ca3PO42. So that lets us cancel out the grams of the calcium phosphate. Now we have the moles of the calcium phosphate, and we can use our mole ratio to get the moles of the sodium phosphate. So this is where we use mole ratio. We have to cancel out the calcium phosphate. So we can see we have 1 mole, our coefficient is 1, whatever that coefficient is, that would go here. So 1 mole of Ca3PO42 for every 2 moles of Na3PO4. The moles of the calcium phosphate now cancel out. And we are not quite finished. We have the moles of the sodium phosphate. We need the grams of the sodium phosphate. So we need 1 more conversion factor. Change those grams to moles. How do we do that? Molar mass. We have to find the grams of sodium phosphate in 1 mole of sodium phosphate. So that means another molar mass calculation. So we have sodium, we have 3 of those, phosphorus we have 1, and oxygen we have 4. From our periodic table, sodium is 22.99, phosphorus 30.97, and oxygen 16.00. Let's add that up. So 3 times 22.99 plus 30.97 plus 4 times 16 equals, and we get 163.94 grams in 1 mole. I'll put that up there. And here our moles canceled out. All the units have canceled out except the unit that we're looking for, the grams of the Na3PO4. And now we look for sig figs. 2 sig figs, 5, unlimited, 5. So our answer gets 2 sig figs. 15 divided by 310.18 times 2 times 163.94 equals. And, oh, that's funny. You get 15.85, so that is 16. So we get 16 grams of sodium phosphate. All right, so our possibilities are, if you're given moles and you're asked for moles, you use mole ratio. You have 1 conversion factor. If you're given grams and you need moles, or you're given moles and you need grams, it's 2 conversion factors. You'll be using mole ratio and a molar mass. And if you're given grams and you're asked for grams, you're going to need 3 conversion factors: a molar mass, a mole ratio, and a molar mass. But just be very careful. Make sure you cancel out your units as you go along. Always use 1 mole when you have grams and moles, and use the coefficients when you have moles and moles in your conversion factor. That's it.